Welcome back to Teaching Statistical Thinking. In our previous videos, we've been focusing on how to describe the distribution of a single variable at a time using graphics, primarily histograms and box plots, and number summaries for center and spread. Today, I'm going to be looking at what happens when we apply arithmetic or mathematical operations to those variables, and how does it change that distribution in terms of its center, spread, and shape. So let's get started. Recall one of our earlier variables that had a 3, 2 4s, 3 5s, 2 6s, and a 7. The histogram looked like this. 1/9 of the area was on 3 and 7, 2/9 on 4 and 6, and 3/9 on 5. The median of that variable was 5. The mean was 5. The range was 4. And the standard deviation was 1.2. Imagine that this variable was part of your grade book for students, and it was the score for each student on a particular quiz. What would happen to the distribution of those quiz scores if you found a grading error that really added 5 points to each student's score? What would happen to the distribution of that variable if you decided you wanted it out of 20 points instead of 10? Those are examples of arithmetic transformations that we're going to be looking at today. We'll also look at one particular transformation called standardizing that's going to come in many times in the subsequent videos. So here we go. Let's start by calling this variable x. The first transformation I'm going to do is suppose we wanted to add 5 points to each data point. Now our 3 would become an 8, 4 would become a 9, 5 would become a 10, 6 would become 11, and 7 would become a 12. Notice what's happened to the distribution. We've shifted it so that the center is now at 10. The median and the mean will both be 10. The range, however, is still 12 minus 8, or stays 4. Notice the average distance to the average also does not change. It stays at a standard deviation of 1.2. So adding a constant to each observation of a variable shifts the mean or the center of the distribution, but it doesn't affect the spread, nor does it affect the shape of that distribution. What if I subtracted 5 points from each observation in our variable? Now the 3 becomes a -2, 4 becomes a -1, 5 is a 0, 6 is a 1, and 7 is a 2. Now we've simply shifted our original variable to the left so that the mean is 0. Because we've got a symmetric distribution, the median is also 0. The range continues to be 4, and the average distance to the mean stays at 1.2. So both for adding or subtracting a constant, it shifts our distribution so that the mean and median change, but the range and standard deviation stay the same, and the shape stays the same. Next, what if we multiply by a constant? What if I multiplied each observation in my data by 2? Now the 3 will become a 6, 4 will become an 8, 5 becomes a 10, 6 becomes a 12, and 7 becomes a 14. Okay. What's happened to the center of my distribution? It's now also doubled, as has the median. Okay. Let's look at the range. 14 minus 6, our range is now 8. So now multiplying by a constant has increased the range by that same constant. And the same thing happens to the standard deviation. The average distance to the mean has now doubled. The last transformation that I want to look at is what if we divide by a constant. Now I'm going to divide each variable in my data set, or observation in my data set, by 2. The 3 becomes 1.5. 4 becomes 2, 5 becomes 2.5, 6 becomes 3, and 7 becomes 3.5. My mean and median have decreased by half. My spread, 3.5 to 1.5, is now 2. It is also decreased by 1/2. And finally, my standard deviation also decreases by half. I want to show you a little bit more generically what's going on. Remember when we calculated the mean of a variable, we said it was the sum of each of the observations divided by the number of observations. Okay. If we take each of our observations by 2, our new mean is going to be 2 times each observation divided by n. We can pull the 2 outside the summation, and we see that we're simply back to 2 times our original mean. And 2 could be any constant that we wanted. Let's also look at how it works for the standard deviation. Remember, for the standard deviation, we said that it was the square root of the summation of each observation, I'm going to call this the standard deviation back, of each observation minus its mean squared divided by the number of observations. Okay. Now what happens when we multiply by the constant 2? Now the standard deviation is going to be the summation of 2 times each of the observations minus, remember, our mean doubled, and then we divide again by the sample size. Okay. We can pull 2 out of the summation, but remember it's squared. So this is going to be 4 times the summation of xi minus the mean squared over n, which simplifies to simply 2 times our original standard deviation. Okay. So when we multiply by a constant, it increases the mean by the same factor, and it increases the standard deviation by that same factor. Division is really multiplication by a fraction. Dividing by 2 is the same as multiplying by a half, so it has the same effect. It will decrease the mean by the factor of a half. It will decrease the standard deviation by a factor of a half. Now there's one more transformation that's going to be very important throughout this course, and it combines some of the transformations we've just used. If I take my original variable and I subtract the mean, in this case 5, okay, and I divide by the standard deviation, which was 1.22, this is called standardizing a variable. If we standardize our original variable by subtracting the mean and dividing the standard deviation, we end up with minus 1.6 for 3, minus 0.8 for 4, 0 for 5, plus 0.8 for 6, and plus 1.6 for 7. Think about what this is doing. It's putting our original variable into how many standard deviations above or below the mean each observation was. 6 is 0.8 standard deviations above the mean. 7 is 1.6 standard deviations above the mean. 4 is 0.8 standard deviations below the mean, and 3 is 1.6 standard deviations below the mean. This is called standardizing a variable. And it's a very important transformation that we'll use often throughout this course. When we standardize a variable, we're centering it to have a mean of 0 and a standard deviation of 1. Okay. In this case, because we have a symmetric distribution, our median is also 0, and our range is 3.2. The transformations I've shown you here all preserve the shape of a distribution. We see that the mean and standard deviations have changed, but the overall shape stays the same. Not all transformations do that, and I'm going to show you one example from our movie data set last time. Remember where we looked at production budget of the 134 movies from our movies data set? The smallest value was $0.2 million, the largest was $250. Recall that that histogram had a very skewed distribution. Most of the values were between 0 and 75 million, but then we had some very large production budgets out at 250 million. There's a particular type of transformation called a log transformation that if we apply it to the production data, it's actually going to change the shape of the distribution. I'm going to very briefly show you how it does that. If we had a movie at $0.1 million, log base 10 of that is at -1. If we had a movie that was at $1 million, log base 10 of 1 is 0. So that movie at 1 million would get mapped to 0. If we had movies at 10 million, about here, log base 10 of 10 is 1, so they get mapped to 1. If we had movies at 100 million, log base 10 of 100 is 2, so they get mapped to 2. What's happening here is movies with relatively small production budgets are getting spread out, whereas movies with very large production budgets are getting squeezed in. Notice the different shapes in those distributions. After we've taken the log transformation, our distribution now is much more symmetric. I bring this up because in many of the variables that you'll see in your data sets, they have a very skewed distribution, and we often take logs to make those distributions more symmetric. You'll understand why later in the course, why that's so important. So that concludes my video on transformations, and pay particular attention and practice at standardizing variables, because that'll come into play a lot in our next video, where we'll be talking about shapes of distributions, specifically bell-shaped curves and normal distributions. So see you then.